Hello, my name is David Escoto, and today I'll be presenting to you my final report from the Climate Winds Weather Analysis, in which I was tasked to predict weather conditions and climate change with machine learning. The motivation for this project was, firstly, recent data shows that weather is becoming increasingly erratic and difficult to predict, with more frequent and severe extreme events. These trends pose growing risks to human safety and critical infrastructure, and Climate Winds is addressing these challenges by applying machine learning models to improve forecasting and resilience. The objectives of this project are firstly to detect weather patterns in Europe that deviate from historical regional norms. The second is to model potential future climate conditions over the next 20 to 50 years based on current trends. Thirdly is to assess whether these atypical patterns are becoming more frequent. And lastly is to identify what the safest regions in Europe will be over the next 25 to 50 years. So in order to accomplish these objectives, I made three thought experiments. The first one is if we use hierarchical clustering, we can go beyond classifying atypical versus typical weather to find actionable categorizations. The second thought experiment was if we use a generative adversarial network, or GAN, as I will call it from now on, to synthesize weather data, we can train a convolution neural network, or CNN, as I will call it from now on, to predict possible future conditions over the next 50 years. And the third thought experiment was that if we optimize a random forest model, we can identify the most important weather features to track and use that information to identify safe living regions. So what are the available machine learning models in order to corroborate these hypotheses based from these thought experiments? The first one is a hierarchical clustering. Uh, Hierarchical clustering categorizes each data point, merging data points or leaves into branches based on similarity, and the result resembles an inverted tree with categories designated by color. The benefits of this is that it generates new classifications from existing data, and it does not require pre-categorization. The second machine learning model that we can use is a random forest. A random forest categorizes data using multiple decision tree models, which classifies data points using true and false processes. A random forest trains each tree on a random sample and averages the results to produce a final prediction. The benefits of this is that averaging processes reduces overfitting, and the second benefit is that it provides clarity through visualizations. The third machine learning model that we can use is the general adversarial network, or GAN. GAN is a generator network that produces artificial data based on real data points. It's a discriminator network, samples both, and attempts to identify accurate data. The generator then uses these results to create more effective fakes, quote unquote. The benefit of this is that it can create weather data that looks and behaves like observed conditions. And the second, sorry, is that it increases the amount of data available for modeling. Finally, the fourth machine learning model that we can use in order to corroborate these hypotheses on the thoughts that I had was a convolution neural network, or CNN. It using hidden layers, the CNN learns the features of a dataset and creates classifications. Hidden pooling layers compress data into average and maximum values, reducing required computing power. The benefits of CNN is first that it effectively analyzes images, including radar-generated graphics, and the second is that it's capable of analyzing complex data. So what will be necessary additional data in order to corroborate these thought experiments using the machine learning models that are required? First will be weather event data with records of extreme weather events across Europe, such as storms, excessive heat, and extreme cold. Second will be radar imagery, such as weather radar data corresponding to regions served by weather stations used in this analysis. Third will be healthcare data, such as information on illnesses, injuries, and deaths attributed to extreme weather. And fourth will be dangerous weather classifications, such as indications of what constitutes hazardous weather to be generated using the above datasets. So let's look at the first thought experiment in classifying weather using hierarchical clustering. Again, the hypothesis was that using hierarchical clustering, we can go beyond classifying atypical versus typical weather to find actionable categorizations. The objective was to identify whether unusual weather patterns are occurring. The approach that I took to assess this was to assess the vitality of this model. I created a dendrogram using existing weather station data. I then employ principal component analysis to reduce number of dimensions for optimal resource use. The results was that the model produced between 2 and 3 clusters consistently, potentially representing binary divisions or low, mid, high divisions. Now, importantly, for this analysis to be valuable, we need to bring in additional types of modeling. I recommend two things. First, running this model on multiple years, seasons, and months of data to compare results, and secondly, using the results to support other, more conclusive model types. Now let's look at the second thought experiment, synthesizing data to improve predictions. The hypothesis was that using a GAN to synthesize weather data, we can train a CNN to predict possible conditions over the next 50 years. The objective was to generate possibilities for weather conditions over the next 25 to 50 years based on current trends. The approach I did to look at this hypothesis was to run a Bayesian optimization on a CNN model to evaluate its accuracy, and then I used a GAN to synthesize realistic weather data. The results were that Bayesian optimization improved the accuracy of the CNN modeling from 12.3% to 92.2%, and the GAN produced weather data with 91% accuracy and 4% loss, suggesting high potential for use with the CNN model. Importantly, we need to acquire recommended radar data and run Bayesian optimization. Specifically, run the optimized CNN model using the GAN generated data and analyze results across years, countries, and regions. Now looking at the third and last thought experiment, assessing regions using a random forest model. The hypothesis was that by optimizing a random forest model, we can identify the most important weather features to track and use that information to identify safe living regions. The objective was to determine the safest places for people to live in Europe over the next 25 to 50 years. The approach I did was to refine hyperparameters for a random forest model using grid and random search methods. Then I compared unoptimized and optimized results of weather data analysis. The results were that optimization increased the accuracy of results from 57.6% to 66.5% when looking at all stations. Running the optimized and unoptimized models allowed us to weigh feature importance in climate analysis. The next steps will be to run optimization processes on additional stations and decades, and then run optimized model on extreme weather data and compare the results to healthcare data to correlate with human well-being. Finally, based on these results of the thought experiments, my recommendations are importantly that data suggests that climate winds will derive the most valuable from investing resources in GAN and CNN optimization to predict weather patterns. This experiment showed that highest jumps in accuracy. The project showed immediate potential for achieving key goals, and this approach has proven real-world success in improving severe weather prediction. The data and algorithms required will be CNN, GAN, and Bayesian optimization algorithms, extreme weather event data, radar imagery, and dangerous weather classifications. The next steps will be to refine the Bayesian optimization of CNN and run CNN with generated data from GAN. Finally, gather and prepare additional data. So thank you very much. That was the results of the project. If you have any questions, just send me an email. And if you want to check out my work, please look at my GitHub. Thank you very much.